When you look at massive mountain ranges or towering volcanoes, it's easy to see them as isolated monuments, but they are actually connected, all driven by a single hidden geological engine grinding away deep beneath the surface. For centuries, the consensus in geology assumed this engine didn't exist. The smartest minds on the planet believed the continents were permanently fixed in place, anchored to a completely static Earth. That assumption held until 1911, when a German meteorologist named Alfred Wegener proposed something radical. He argued that a massive supercontinent called Pangaea had slowly broken apart, with the landmasses drifting across the globe to their current positions. Wegener found that fossils of the exact same ancient plants and animals were scattered across continents separated by thousands of miles of ocean. But despite these matches, he couldn't explain how millions of tons of solid rock could actually move. Without a physical mechanism to push the land, the scientific community rejected his theory. Wegener eventually died on an expedition in Greenland, never knowing the true source of the movement. The answer was never going to be found on land. To figure out what was driving the continents, scientists had to look down into the uncharted depths of the ocean floor. The breakthrough came by accident. During World War II, navies developed sonar technology to bounce sound waves off the ocean floor, hunting for enemy submarines. They gathered data that would reveal the seafloor's true structure. In the 1950s, scientists Marie Tharp and Bruce Heezen compiled sonar pings to create the first accurate bathymetric map of the Atlantic Ocean. It revealed a massive underwater mountain range, a mid-ocean ridge perfectly mirroring the jagged coastlines of the Americas and Africa. Looking at these structures, a geologist named Harry Hess proposed a theory called seafloor spreading. He suggested that hot magma from deep underground was rising through this central ridge, cooling into new crust and physically pushing the continents apart. This expansion leaves a measurable trail. First, active fractures match the continental coastlines. Second, rock is youngest at the ridge, getting progressively older outward. Third, sediment layers grow thicker toward the continents, because older rock had millions of extra years to collect debris. All of this physical data supported the idea of an expanding seafloor, but scientists still needed recorded proof of the movement to convince the remaining skeptics. The proof was hidden in the way our planet behaves internally. Earth's liquid outer core acts as a giant generator. Molten metals swirl, producing our global magnetic field. Periodically, the magnetic poles completely flip. When hot liquid magma erupts at the mid-ocean ridge and hits the cold seawater, it freezes into rock. The iron minerals inside that magma act like tiny compass needles, locking into place and recording whatever the Earth's magnetic polarity is at that exact moment. In 1963, Fred Vine and Drummond Matthews used magnetometers to scan the ocean surface. They found the seafloor was covered in alternating stripes of normal and reversed magnetism, recording every pole flip over millions of years. If you look at the stripes on the left side of the ridge, they perfectly match the width and polarity on the right. That symmetrical mirroring is only possible if the seafloor is splitting down the middle and actively expanding outward. The ocean floor was acting as a giant tape recorder, and the recording was finally undeniable. One question remained. If volcanic activity is tied to these ridges, why do island chains like Hawaii form in the middle of a tectonic plate, thousands of miles away from any boundary? Geologist J. Tuzo Wilson explained these anomalies with the concept of mantle plumes or hotspots. These are stationary jets of incredibly hot magma that well up from deep inside the Earth and punch through the crust. Because the hotspot stays still while the tectonic plate above it moves laterally, the magma burns a sequential trail of increasingly older volcanic islands into the surface, acting like a geological conveyor belt. Wilson also identified transform faults, the perpendicular cuts along ridges, to account for the varying rates of expansion. These observations connected the final pieces of oceanic geology. Wegener's drifting continents and Hess's seafloor spreading eventually merged into a single framework, the theory of plate tectonics. The rigid lithosphere and the ductile asthenosphere function together as a massive planetary recycling engine. As brand new crust is born from the mid-ocean ridges, old, dense rock is pushed back down into deep subduction zones to be melted away. It is a continuous churning cycle of creation and destruction that keeps the Earth dynamic.